Hello there. Let your breathing slow. Let the weight of the day settle into whatever surface is holding you, and let that surface hold you completely. You don't need to carry anything right now. The water is doing that. Tonight, we are going to the sea. Not quickly, not to the shore, where the waves are loud and the light is bright and everything is in motion. We are going deeper, past the sunlit shallows, past the twilight zone where the last blue light fades to nothing, down through the cold and the pressure and the extraordinary darkness of the deep ocean, all the way to the seafloor. We are going to spend tonight in the company of the planet's largest habitat, a world that covers 71% of all the surface on Earth, that contains 97% of all the water on Earth, and that remains, in its deepest parts, more thoroughly unexplored than the surface of the Moon. Tonight we will visit 100 of the most quietly remarkable facts about the ocean, its depth and its darkness, its bioluminescent creatures and its slow-moving currents, its hydrothermal vents and its coral cathedrals, its ancient chemistry and its patient, tidal rhythms. We will not rush. The ocean does not rush. It has been here for 4 billion years, and it will be here long after the last human voice has asked a question about it. The water is all around you. The dark is soft. Let's go down. The ocean covers approximately 361 million square kilometers of the Earth's surface, roughly 71% of everything available. That number is large enough to feel abstract until you consider what it means concretely. If you picked a random point on the surface of the Earth, you would land in ocean more often than not, and the average depth of that ocean is about 3,688 meters. By volume, the ocean contains about 1.335 billion cubic kilometers of seawater, a quantity so large it is essentially incomprehensible in human experiential terms. The Pacific Ocean alone is larger than all the land on Earth combined. The ocean is not an add-on to the terrestrial world. It is the dominant feature of this planet's surface, and every account of life on Earth that doesn't begin there is starting in the middle of the story. The water in Earth's oceans is ancient, most of it delivered to the young planet more than 4 billion years ago by a combination of volcanic outgassing and the impacts of water-bearing asteroids and comets during the heavy bombardment period of the early solar system. By roughly 3.5 billion years ago, a global ocean was established, and within it, the first life on Earth appeared. Not on land, not in air, but in water, in the chemistry of a warm, mineral-rich sea. Every living thing on Earth today is descended, without interruption, from those first aquatic organisms. The ocean didn't simply host life's origin. It provided the chemistry, the protection from ultraviolet radiation, and the energy sources that made life chemically possible in the first place. The water you are largely composed of has cycled through the ocean, the atmosphere, and living organisms many times over the history of this planet. The ocean is divided by oceanographers into 5 distinct vertical zones based on the penetration of sunlight and the conditions that prevail at different depths. The sunlit or photic zone extends from the surface to roughly 200 meters, the range within which photosynthesis is possible. Below it lies the twilight or mesopelagic zone from 200 to 1,000 meters, where some light still permeates but not enough for photosynthesis. The midnight or bathypelagic zone extends from 1,000 to 4,000 meters in complete darkness. The abyssal zone reaches from 4,000 to 6,000 meters across the broad, flat plains that cover much of the deep sea floor. And finally, the Haddle Zone occupies the ocean trenches, those narrow, canyon-like depressions in the seafloor that reach beyond 6,000 meters, the deepest environments on the planet. Each zone has its own characteristic pressure, temperature, chemistry, and community of organisms adapted to its particular combination of conditions. Pressure in the ocean increases by approximately 1 atmosphere, 1 bar, roughly equivalent to the weight of the entire atmosphere above sea level for every 10 meters of depth. At 100 meters, the pressure is 10 times that at the surface. At 1,000 meters, it is 100 times greater. At the bottom of the Challenger Deep in the Mariana Trench, the deepest known point in any ocean, at approximately 10,935 meters, the pressure exceeds 1,000 atmospheres, or about 100 megapascals. This is the equivalent of having 50 jumbo jets stacked on top of every square meter of your body. Life has adapted to function normally under these conditions, using internal body pressures equal to the external water pressures to avoid being crushed and relying on biochemical modifications, different membrane lipid compositions, stabilizing molecules called piezolites, that keep enzymes functional and membranes fluid under conditions that would destroy the corresponding molecules at the surface. Light penetrates the ocean's surface with remarkable swiftness. Within the first 10 meters, approximately half of all incoming solar radiation has already been absorbed, much of it in the infrared range, which is why the very top of the water column feels warm, while even a shallow dive quickly brings you into noticeably cooler water. Red wavelengths are absorbed first, within the uppermost few meters, which is why close-up photographs taken underwater without artificial light tend toward blue and green. There is simply no red light remaining to reflect off red surfaces. Yellow and orange follow within the first few tens of meters. By 200 meters, even blue light, the most penetrating wavelength in seawater, has been reduced to less than 1% of its surface intensity. Below that, the ocean is not merely dim, it is dark in a way that no terrestrial environment ever is. A darkness with no seasonal variation, no night and day, no flicker of any light from above. The photic zone, the uppermost layer of the ocean where sunlight is sufficient for photosynthesis, is the most biologically productive region of the sea, but it is also one of the thinnest. In a global ocean averaging nearly 4 kilometers deep, the photosynthetically active layer occupies the top 200 meters, roughly 5% of the total depth. Within this narrow layer, phytoplankton, microscopic, single-celled photosynthetic organisms, produce approximately half of all the oxygen in Earth's atmosphere, fixing carbon dioxide as a byproduct, just as land plants do. These organisms are too small to see individually, but their collective biomass constitutes the base of the marine food web, and their collective photosynthesis is one of the most significant biological processes on the planet. The ocean breathes for you, in part with organisms so small that a teaspoon of surface seawater contains millions of them. Salinity, the concentration of dissolved salts in seawater, averages about 35 parts per thousand by mass, meaning that every kilogram of seawater contains roughly 35 grams of dissolved salts. Sodium chloride, ordinary table salt, makes up about 85% of this. The remainder includes magnesium, sulfate, calcium, potassium, and dozens of other ions in smaller concentrations. This salinity is not uniform. It varies with evaporation, which concentrates salts, precipitation, which dilutes them, freshwater input from rivers, and the formation or melting of sea ice, which excludes salt during freezing, concentrating brine in the surrounding water. The saltiness of the ocean has remained roughly constant for hundreds of millions of years, balanced by the delivery of dissolved minerals from weathering on land and the removal of ions through seafloor mineral formation. The ocean's chemistry is in a slow geological equilibrium, not perfectly static, but stable on ocean-crossing timescales. Temperature in the ocean is not uniformly distributed with depth. The surface ocean, warmed by the sun, forms a relatively warm upper layer that sits atop much colder deep water. The boundary between these two layers, the thermocline, is a zone of rapid temperature decrease with increasing depth, and it acts as a physical barrier that resists vertical mixing between the warm surface and cold deep waters. In tropical ocean regions, the thermocline is sharp and persistent, sitting at roughly 200 to 1,000 meters depth. Below the thermocline, ocean temperature continues to decrease with depth, eventually reaching between 1 and 4 degrees Celsius in the deepest abyssal plains. A chill that has persisted unwarmed by sunlight for thousands of years. This cold, dense deep water was last at the surface in the polar regions, where it sank, and has been slowly circulating through the deep ocean ever since, carrying its cold temperature and its dissolved gases on a journey that takes centuries to complete. One of the most remarkable features of open ocean biology is a phenomenon called the deep scattering layer, a dense concentration of marine organisms that distributes itself at depths of roughly 200 to 1,000 meters during the day and migrates upward toward the surface at night. The layer was first detected by echo sounders during the Second World War, when operators noticed a false bottom appearing on depth-sounding records at a depth shallower than the actual seafloor, and then disappearing again at night. What they had discovered was a vast mobile curtain of creatures, lanternfishes, shrimp, squid, and other mesopelagic organisms, performing the largest daily migration on Earth. Each evening, billions of animals ascend hundreds of meters to feed on the plankton-rich surface waters. Each dawn, they descend again into the dim safety of the twilight zone. The energetics of this migration transfer enormous quantities of carbon and nutrients from the surface to the deep ocean in a slow biological rain. The mesopelagic zone, the twilight layer between 200 and 1,000 meters, is one of the least studied and most ecologically important regions of the ocean. Despite the near-total darkness, it is populated by an extraordinary diversity of organisms adapted to life. Many of them produce their own light through bioluminescence. Many have evolved enormous eyes to maximize the collection of whatever faint photons remain. Some have developed transparent bodies that make them nearly invisible in the filtered light, while others are jet black, absorbing all available light to avoid detection. The mesopelagic zone is thought to contain more fish biomass than all of the world's commercial fisheries combined, though catching and counting organisms in this difficult-to-access environment is challenging. It is a zone defined by in-betweenness, between the light and the dark, between the surface and the deep, and it is full of lives that have arranged themselves around this defining condition with remarkable creativity. The thermohaline circulation, sometimes called the ocean conveyor belt, is a planet-scale circulation of seawater driven by differences in temperature and salinity rather than by wind. Cold, salty water is denser than warm, fresh water, and in the North Atlantic and around Antarctica. Surface water, chilled and concentrated by evaporation or ice formation, becomes dense enough to sink to the ocean floor, initiating a slow, deep circulation that travels from basin to basin over centuries and millennia. This circulation carries cold, oxygen-rich deep water through the Atlantic, Indian, and Pacific Ocean basins and returns surface water through a global network of upwelling zones and warm surface currents. The Gulf Stream, the warm current that moderates the climate of Western Europe, is a surface expression of this deep circulation. The entire system transfers enormous quantities of heat from the tropics toward the poles and is one of the primary mechanisms by which the ocean regulates Earth's climate. The seafloor is not a flat, featureless plain. It is among the most topographically varied surfaces on the planet, shaped by the same plate tectonic forces that raise mountain ranges on land, but operating over larger areas and with different expressions. Mid-ocean ridges, submerged mountain ranges marking the boundaries where tectonic plates diverge, extend for more than 65,000 kilometers across all the ocean basins, forming the longest mountain chain on Earth. Seamounts, underwater volcanoes that rise from the seafloor but do not reach the surface, number in the tens of thousands and act as islands of biodiversity, their slopes concentrating nutrients and shelter for deep-sea communities. Ocean trenches, where one tectonic plate dives beneath another in a process called subduction, form the deepest points in the ocean, their narrow, steep-sided profiles extending to depths that place them beyond the reach of all but the most specialized research vehicles. The continental shelves, the gently sloping extensions of the continents beneath the ocean, typically extending to a depth of about 200 meters before dropping steeply to the deep seafloor, occupy only about 8% of the total ocean area, but support an overwhelming proportion of its most accessible marine life. Here, in relatively shallow water over sediment-rich bottoms, light reaches the seafloor, nutrients are replenished by river input and upwelling, and the physical structure of the bottom provides the variety of habitats required by the widest diversity of species. Coral reef, kelp forests, seagrass meadows, and soft sediment communities of worms, clams, crabs, and flatfish are all creatures of the continental shelf. The vast open ocean is by comparison a desert, enormous in area but sparse in life per unit volume, its nutrients driven down by the stratification that keeps warm surface water separated from the rich, cold water below. Life in the sea crowds toward the edges, the shallows, and the places where the deep meets the light. A coral polyp is a small, soft-bodied animal belonging to the phylum Cnidaria, the same group that includes jellyfish and sea anemones. The polyp attaches itself to a hard substrate, secretes a cup-shaped skeleton of calcium carbonate around its lower body, and extends its tentacles into the water to capture zooplankton that drift past. In most reef-building corals, the polyp lives in extraordinarily close association with single-celled algae called zooxanthellae, which reside within the cells of the polyp's tissue, not attached to the outside, but embedded within the animal itself. It is the foundation of everything a coral reef is. The zooxanthellae photosynthesize using sunlight, filtering through the shallow water, producing sugars and oxygen that supply the coral polyp with the majority of its energy needs. In return, the coral provides the algae with a protected environment and access to the carbon dioxide and nutrients produced by the animal's own metabolism. The calcium carbonate skeleton secreted by each coral polyp accumulates across thousands of individual animals, generation after generation of a reef. Individual coral colonies grow at rates that vary by species. Branching corals can add several centimeters per year. Massive brain corals may grow only a centimeter, or two annually. The oldest known colonies of some massive coral species are centuries old, their growth a slow geological accumulation of biological labor. The Great Barrier Reef, the largest coral reef system on Earth, stretching for more than 2,300 kilometers along the northeastern coast of Australia, has been growing in its current form for approximately 6,000 to 8,000 years, since sea levels stabilized after the last ice age. But the limestone bedrock underlying it contains older coral material that extends millions of years into the past, a continuous geological record of biological productivity laid down in what was, for all that time, shallow, warm, sunlit sea. The Great Barrier Reef is large enough to be visible from space. It encompasses approximately 344,400 square kilometers, an area larger than the United Kingdom, and consists of roughly 2,900 individual reefs and 900 islands. It provides habitat for more than 1,500 species of fish, 4,000 types of mollusk, 240 species of bird, 30 species of whale and dolphin, and 6 of the world's 7 sea turtle species, among thousands of other invertebrate and plant species. Its biodiversity is a function of its physical complexity. The three-dimensional structure of the reef provides an extraordinary variety of microhabitats, niches, and shelter configurations, allowing many species to occupy the same space by partitioning it along different axes. Some species using crevices, some living on bare rock, some grazing on algae, some hunting in the water column above the reef. The reef is not simply a structure that life inhabits. It is a structure that life built and continues to build from the inside. The relationship between a coral polyp and its zooxanthellae is sensitive to water temperature in a way that has become one of the defining ecological vulnerabilities of coral reefs in the current era. When water temperature rises above the range that zooxanthellae can tolerate, typically by only 1 to 2 degrees Celsius, above the seasonal maximum, sustained for several weeks, the algae begin producing toxic reactive oxygen compounds that damage the coral cells. The coral's response is to expel the algae from its tissue. Without the zooxanthellae, the coral loses its main energy source and its color, turning white in a process called coral bleaching. A bleached coral is not immediately dead. It is stressed and starving, and if temperatures return to normal within a few weeks, the zooxanthellae can recover. If the thermal stress is prolonged, the coral dies. The skeletal structure remains white and bare, and the community of organisms that depended on it begins to disintegrate. Ocean acidification, the ongoing decrease in the pH-ide seawater caused by the absorption of atmospheric carbon dioxide, poses a chemical challenge to coral reefs that operates more slowly than bleaching, but is in some ways more fundamental. Seawater chemistry determines how easily marine organisms can extract calcium and carbonate ions from the water to build their shells and skeletons. As more CO2 dissolves into the ocean, it reacts with water to form carbonic acid, which releases hydrogen ions and reduces the concentration of carbonate ions. At lower carbonate saturation, corals must expend more energy to calcify, grow more slowly, and produce skeletons that are weaker and more porous than those formed in historically normal ocean conditions. At sufficiently low carbonate saturation, conditions projected to occur in parts of the tropical ocean by the end of this century under high emission scenarios, net calcification may become impossible and existing reef structures may begin to dissolve faster than they are rebuilt. The reef that took 6,000 years to grow could not survive such conditions. Coral reefs are sometimes called the rainforests of the sea. and the comparison, while often dismissed as a cliché, captures something real about their biological role. Despite covering less than 1% of the ocean floor, coral reefs are estimated to support roughly 25% of all known marine species. This extraordinary concentration of diversity in a small area reflects the reef's structural complexity, its productivity, and its provision of shelter and food resources in a part of the ocean that would otherwise be relatively sparse in nutrients. The warm, sunlit, low-nutrient tropical waters where reefs thrive, the blue deserts of the open ocean, become, over the reef, locally rich in nutrients and life through the tight internal recycling of materials that the reef ecosystem performs. What the reef imports from the surrounding ocean is meager. What it produces within itself, through the patient cycling of carbon, nitrogen, and phosphorus among its thousands of component species, is extravagant. Many coral species reproduce through one of the most remarkable synchronized biological events in the natural world: mass coral spawning. On 1 to a few nights per year, typically coordinated with the lunar cycle and timed to the warming of water temperatures, vast numbers of coral polyps simultaneously release gametes, eggs and sperm, into the water in a blizzard of pink and white bundles. These buoyant bundles rise to the surface, where the gametes are fertilized by chance encounters with those from other coral colonies of the same species, and the resulting larvae drift in the plankton for days to weeks before settling onto a suitable substrate and beginning to grow a new colony. The coordination is achieved entirely through environmental cues: moonlight, water temperature, the length of daylight, with no communication between colonies. Yet across hundreds of kilometers of reef, the release is synchronized to within hours. On the Great Barrier Reef, the mass spawning event produces so much material that it is visible in satellite imagery. Parrotfish are among the most ecologically important inhabitants of a coral reef, and also among the most visually extravagant. Their fused beak-like teeth giving them exactly the appearance suggested by their name, their scales displaying blues, greens, pinks, and purples in patterns that seem too vivid to be practical. What parrotfish do on the reef is not merely decorative. They scrape algae from coral surfaces using their beaks, in the process ingesting large amounts of the calcium carbonate skeleton. This material passes through their digestive systems and is excreted as fine white sand. A significant proportion of the soft, white sand found on tropical beaches and reef lagoons is, in a very direct biological sense, parrotfish excrement. Large parrotfish can produce hundreds of kilograms of sand per year. Their grazing also prevents algae from overgrowing and smothering corals, maintaining the balance between coral growth and algal colonization that keeps a healthy reef looking the way it does. The cleaning stations found on coral reefs are a living demonstration of the depth and specificity of ecological relationships that reef communities develop. Certain species of small fish, particularly wrasses of the genus labroids, establish and defend specific sites on the reef where they perform a service of extraordinary value, removing parasites, dead tissue, and food debris from the bodies, gills, and even the open mouths of larger fish that visit the station. The larger fish, including species that would normally eat smaller fish immediately, approach the cleaning station and adopt a specific posture, often hovering nearly motionless, that signals their intention. The cleaner recognizes the signal and begins working, moving over the surface of the larger fish with a methodical thoroughness. The relationship is not simply tolerated from above. Large predatory fish actively seek out cleaning stations when parasite, and experiments removing cleaner wrasses from sections of reef result in visible increases in parasite loads and skin lesions in the fish populations and fisher populations. That remains stochastic, etc. The reef at night is a different world from the reef by day, populated by different organisms doing different things in the same physical space. By day, the colorful fish species that visitors associate with coral reefs are active, grazing, hunting, displaying, competing. As light fades, many of these species retreat into crevices and under coral heads, their colors fading slightly as they sleep, their metabolism slowing. From the same crevices and ledges, the night shift emerges. Lobsters and crabs picking their way across the seafloor. Basket stars and feather stars extending long feathery arms to filter feed from the current. Octopuses hunting across open reef pavement with a fluid, unhurried intelligence. Moray eels leave their daytime retreats and hunt through the dim water. Flashlight fish, a species with light-emitting organs beneath each eye, blink their bioluminescent patches in patterns used for intraspecific communication and the detection of prey. The architecture of the reef does not change. Its tenants rotate in shifts, the living structure cycling through its daily rhythms as reliably as any clock. Seagrass meadows, often found adjacent to coral reefs in shallow coastal waters, form one of the most productive and ecologically significant marine habitats on the planet, and one of the most overlooked. Seagrasses are true flowering plants, not algae, the only flowering plants to have fully returned to marine life. Their flowers pollinated underwater, and their roots anchoring them in sandy and muddy sediments in shallow, sunlit coastal zones. Their meadows provide food for sea turtles and dugongs, which graze on the blades directly, shelter for juvenile fish, seahorses, and invertebrates, nursery habitat for many commercial fish species, and a significant carbon sink, sequestering organic carbon in their sediments at rates per unit area that exceed those of most terrestrial forests. They also stabilize sediments, reducing coastal erosion and improve water clarity by trapping suspended particles. Seagrass meadows are being lost globally at significant rates due to coastal development, water quality decline, and warming, quietly without the attention that coral bleaching receives. To lie above a coral reef in shallow, clear water, to float without movement on the surface, and look down at the three-dimensional world below, is to experience a quality of visual complexity and color density that has no parallel in any terrestrial landscape. The structure extends in every direction. Coral heads and walls and crevices, curtains of fan coral moving in the gentle surge, schools of fish shifting in coherent masses, like a single organism made of many, individual creatures going about lives of extraordinary particularity within the general business of the reef. The light filters down in shifting shafts, picking out the iridescence of a wrasse's scales, the deep red of a sea fan, the startling blue of a tiny damselfish defending its patch of algae with a ferocity entirely disproportionate to its size. Every square meter of a healthy reef contains more biological information than any human mind can process in a single observation. You can float above it for an hour and still feel that you have barely begun to see it. Bioluminescence is produced through a chemical reaction whose essential components appear, with variations across the many lineages of organisms that have independently evolved the capability. The reaction involves two classes of molecule, a light-emitting compound called luciferin and an enzyme called luciferase that catalyzes its oxidation. When luciferin is oxidized in the presence of luciferase, it enters an excited electronic state and then releases the excess energy as a photon of visible light, typically blue or green, the wavelength that travel farthest through seawater. The reaction produces almost no heat. It is sometimes called cold light to distinguish it from the thermal emission of a flame. The efficiency of the reaction is extraordinary. Some bioluminescent organisms convert nearly all the chemical energy consumed into light, with almost no wasted heat. This is far more efficient than any artificial light source in common human use, and has inspired ongoing research into bioluminescent compounds for applications in medical imaging and biosensors. The most commonly encountered bioluminescence in the ocean belongs not to fish or squid, but to dinoflagellates, single-celled, microscopic organisms that are among the most abundant planktonic life forms in the surface ocean. Dinoflagellates produce light in response to mechanical disturbance. A wave breaking, a bow wave from a ship, the passage of a swimming fish, a hand swept through dark water on a warm night. The flash is brief, lasting only fractions of a second, and blue-green in color. In calm conditions in bays with dense dinoflagellate populations, the phenomenon becomes spectacular. Each breaking wavelet sparkles with cold fire. Every footfall in the shallows leaves a glowing print, and a swimmer moving through the water trails living light from every surface of their body. The light serves the dinoflagellate to some extent as a burglar alarm. The flash attracts the predators of the zooplankton that graze on the dinoflagellates, deterring the grazer. The anglerfish, a deep-sea predator, so distinctive that it has become one of the most recognizable creatures of the dark ocean, uses bioluminescence as a lure in one of nature's most elegant traps. The female of many anglerfish species carries above her head a modified dorsal spine, the elysium, tipped with a fleshy organ called the esker, which glows with light produced by bioluminescent bacteria living within it. The esker sways in the dark water, its light mimicking, to the eyes of curious or hungry prey, the glow of a smaller bioluminescent organism. Prey approaching the lure comes into range of the anglerfish's cavernous, fang-equipped mouth. The anglerfish does not chase. It barely needs to move. It holds its lure in the dark and waits, relying on the curiosity or hunger of its prey to close the distance between them. In the deep ocean, where food is scarce and metabolic budget is everything, this economy of effort is a profound evolutionary advantage. Counter-illumination is a bioluminescent camouflage strategy used by a remarkable variety of mesopelagic and deeper-dwelling organisms. The principle exploits the fact that the only significant light source in the deep ocean above the aphotic zone is the faint, downwelling blue light coming from above. A fish or squid swimming in this zone casts a shadow downward. Its silhouette is visible from below against the slightly brighter background of the water above, making it detectable to predators located below and looking up. Counter-illuminating animals produce bioluminescent light from their ventral surfaces, their undersides precisely matching the intensity and color of the downwelling light from above. Their silhouette is effectively erased. A predator looking up sees not a dark shape against a lighter background, but a uniform field of blue light with no interruption. The matching is sometimes adjustable, the animal modulating its own emitted light in response to changes in ambient light intensity. It is camouflage executed in light rather than pigment. The burglar alarm hypothesis, the idea that bioluminescent flashes serve as a defense against predators by attracting the predator's own enemies, applies not only to dinoflagellates but to a variety of larger marine organisms. A small fish or shrimp that bioluminesces when threatened by a predator may be alerting larger predators to the presence of that predator. in effect converting its attacker into a target. The hypothesis has been tested experimentally using tethered prey animals, attaching bioluminescent and non-bioluminescent variants to lines and measuring the rate at which their predators are themselves consumed. The results are broadly consistent with the hypothesis. Being near a bioluminescent prey item in the dark ocean is a more dangerous position for a predator than being near a non-glowing one. The light that an animal produces under threat is not simply a signal of distress. It is a call for intervention, a very specific request, sent in photons to whatever else is out there in the dark. Some deep-sea organisms use bioluminescence not to attract or to hide, but to produce patterns that appear to function as species recognition signals, a form of visual communication in an environment where all other visual communication cues were stripped away by the darkness millions of years ago. Certain species of ostracod, tiny crustaceans roughly the size of a sesame seed, produce species-specific patterns of bioluminescent flashes during courtship, with males rising from the seafloor at specific times and emitting pulse trains unique to their species. Females resting on the substrate below respond to the correct species-specific pattern. In enclosed bay environments where multiple ostracod species coexist, these different pulse trains keep species separate despite their close proximity. The chemical light functioning as the equivalent of a bird's song or a firefly's flash, a channel of communication so specific that it admits the right partner and excludes all others. Flashlight fish, belonging to the family Animalipidae, carry beneath each eye a large bean-shaped light organ containing dense colonies of bioluminescent bacteria. The light is continuous rather than flashing, produced by the bacteria's own metabolic activity rather than by any chemical pulse from the fish itself. The fish controls its light not by turning it on and off, but by blinking, either rotating the light organ so the glowing surface faces inward, or pulling a lid across it, creating a controllable intermittent light source. Flashlight fish are found in the mesopelagic zone and in reef crevices at night, and they use their light for navigation, for attracting the zooplankton they feed on, and for communication with other flashlight fish. The blinking patterns observed in schools of flashlight fish at night appear to serve a social coordination function, allowing individuals to remain in contact with the group without the risk of visual exposure to predators that constant, steady light would entail. Sea pens. Colonial marine invertebrates, related to corals, anchored upright in soft sediment substrates on the deep and shallow sea floor alike, include many bioluminescent species that produce some of the most visually striking light displays in the ocean when disturbed. When a disturbance propagates along the colony, a touch, a wave of current, the luminescence travels in a pulse from the point of contact outward through the entire structure, rippling along the feathery branches of the colony in a wave of blue-green light that fades as quickly as it arrives. The function of this propagating light pulse in sea pens is not entirely resolved. It may serve as a startle response broadcast across the colony. It may attract the predators of animals that disturb sea pens. In any case, it is one of the most purely beautiful expressions of bioluminescence in the ocean. Slow, cold, perfectly blue, briefly illuminating a creature that otherwise lives in complete and unbroken darkness. The vampire squid. Vampire squid from hell. A name given before it Teuthus infernalis. The vampire squid from hell, a name given before its genuinely tranquil feeding habits were understood, is neither a true squid nor an octopus, but occupies its own taxonomic order, and is one of the more impressively bioluminescent animals in the deep ocean. Nearly every surface of its body that faces outward is covered with light-producing photophores, organs that produce controlled bioluminescent flashes of varying color and intensity. Its arms are tipped with glowing structures. Its body carries photophores in complex arrangements that researchers believe are used for camouflage and intraspecific communication. Most remarkably, the vampire squid can turn its entire body into a field of light or darkness at will, flashing brightly to confuse a predator, then going dark and retreating while the predator's vision adjusts. In the absolute dark of the bathypelagic zone, this flexibility of light production is a complete and comprehensive visual defense system. Bioluminescence is far more prevalent in the ocean than most people appreciate. Surveys of deep-sea organisms using submersible cameras suggest that more than 70 to 80% of deep-sea organisms are capable of producing bioluminescent light. This figure applies across a remarkable range of taxonomic groups: fish, squid, shrimp, copepods, jellyfish, siphonophores, worms, brittle stars, sea cucumbers, and bacteria. Light production in the deep ocean is not an exotic specialization of a few strange creatures. It is the norm, the dominant mode of visual expression in a world where the only alternative is silence. The deep ocean, often described as a world of absolute darkness, is perhaps more accurately described as a world of self-generated light. Dim, intermittent, chemical rather than thermal, but real and varied, flashed in warning, dangled as a lure, shone as camouflage, pulsed as a signal, and sometimes, in the case of the dinoflagellate, simply sparked by the passing of something larger moving through the water. The siphonophore, known as Irena richardi, a colonial gelatinous organism distantly related to jellyfish, was observed using bioluminescent lures of red light, which was unexpected. Most deep-sea bioluminescence is blue or green, as these wavelengths travel farther through seawater, and most deep-sea animals have visual pigments sensitive to blue light. Red light is absorbed rapidly by seawater and was long thought to be effectively invisible at depth. But the prey of Irena richardi, small mesopelagic fish, possess visual pigments sensitive to red wavelengths, adapted perhaps to detect the bioluminescence of the dinoflagellates they feed upon. The siphonophore's red lure appears to be precisely tuned to the visual sensitivity of its specific prey, a light that most organisms in the environment cannot see, but one particular target species can, exploiting not the general visibility of the signal, but its specificity. It is targeting, in photons, a single audience. There is something about the idea of bioluminescence, of organisms making their own light in the cold and dark of the deep sea, glowing blue-green in water that has never seen sunlight. That settles into the mind differently from other biological facts. It is not simply a physiological capability. It is a kind of eloquence, the capacity to speak in the only available medium, to make something visible where nothing was visible before, to call and answer across distances measured in meters in a world where a meter of visibility is a significant range. The deep ocean's bioluminescence is not silence lit up. It is the language of organisms that have been in the dark for so long that they learn to carry light with them. Every flash is a sentence. Every glowing fin or dangling lure or sparking wave is part of a conversation that has been going on, uninterrupted, for hundreds of millions of years. In the coldest, most patient dark on the surface of this planet, hydrothermal vents form at divergent tectonic plate boundaries, the mid-ocean ridges, where seawater percolates down through cracks in the seafloor into the heated rock below. and where the geological heat of the earth meets and reacts with the chemistry of the water. Seawater descending into the crust is heated to temperatures that can exceed 400 degrees Celsius, far above the boiling point at surface pressure, but held in liquid form by the immense pressures at depth. This superheated water leaches minerals from the surrounding rock: hydrogen sulfide, methane, iron, manganese, copper, and zinc, among many others, and rises back toward the seafloor, emerging at the vent field in a plume of hot, chemically enriched fluid. The plumes interact with the near-freezing ambient deep water, and the dissolved minerals rapidly precipitate from solution as the temperatures equilibrate, building up the mineral chimneys, black smokers and white smokers that give vent fields their characteristic and otherworldly appearance. The water exiting a black smoker vent can reach temperatures of between 300 and 400 degrees Celsius, and it is black because it is laden with iron and sulfide minerals that precipitate immediately upon contact with the surrounding cold seawater, forming the characteristic dark plume. The chimneys themselves, built from these same precipitating minerals, primarily anhydrite, sulfides of iron, copper, and zinc, can grow at remarkable rates, several centimeters per day in active vent systems, reaching heights of tens of meters and widths of several meters in mature structures. They are fragile relative to their size, prone to collapse under their own weight or the mechanical force of the vent fluid. And when they fall, new chimneys begin to grow from the base. Vent fields undergo continuous cycles of construction and collapse, the mineral architecture of the seafloor in constant slow renovation driven by the heat and pressure of the Earth's interior working its way toward the water above. The food web at a hydrothermal vent has no sunlight at its foundation. In the sunlit ocean, photosynthesis is the primary pathway through which energy enters the biological community. Sunlight drives the conversion of carbon dioxide and water into organic matter that all other organisms then consume in various sequences. At a hydrothermal vent, there is no sun. The primary pathway is chemosynthesis, the metabolic process by which certain microorganisms extract energy not from light, but from the oxidation of reduced chemical compounds: hydrogen sulfide, methane, hydrogen gas, expelled by the vent. These chemototrophic bacteria and archaea fix carbon dioxide into organic matter using chemical energy in the same way that photosynthetic organisms use light energy, and they form the productive base of the entire vent ecosystem. Every organism that lives in and around a hydrothermal vent, every tube worm and vent fish and vent crab, ultimately derives its energy from the heat and chemistry of the Earth's interior, not from the sun. Giant tube worms, Riftia pacutilla, are among the most immediately striking inhabitants of hydrothermal vent communities in the Eastern Pacific. They can grow to more than 2 meters in length, living in white chitinous tubes anchored to the basalt seafloor around active vents, extending a brilliant red feathery plume, rich in hemoglobin, hence its color, into the vent fluid to absorb hydrogen sulfide and oxygen from the surrounding water. They have no mouth, no gut, no digestive system of any kind. They are entirely dependent for nutrition on a dense community of chemototrophic bacteria that live within a specialized organ in their body, called the trophosome, a spongy vascularized tissue that accounts for more than half the worm's body mass and houses billions of bacterial symbionts. The bacteria oxidize the hydrogen sulfide that the worm delivers to them and produce organic carbon that the worm absorbs as food. The relationship is obligate on both sides. The worm cannot live without the bacteria. The bacteria cannot access the resources they need without the worm's physiology. Without the worm's physiology, The growth rates of Riftia pachypetala are among the fastest recorded for any marine invertebrate. Individuals can grow from juvenile to full adult size in as little as 18 months, adding more than 85 centimeters in their first year under optimal conditions near active vents. This rapid growth reflects both the extraordinary nutritional productivity of the chemosynthetic symbiosis within the trophosome and the instability of the vent environment. Vent systems can shut down with little notice when the geological activity driving them diminishes or when a collapse blocks the vent opening, and the organisms that depend on them must be able to colonize new vent sites quickly when they form. The ecological community at a vent is not a stable, climax ecosystem of the kind that develops in old-growth forests. It is a community adapted to disturbance and impermanence, tuned to bloom quickly wherever the conditions permit, and to disperse its offspring to reach the next opportunity when the current one closes. Vent shrimp of the family Alvinocarididae, particularly the species Rhymicaris exoculata, found in abundance at hydrothermal vent fields along the mid-Atlantic ridge, have evolved one of the most unusual visual systems in the animal kingdom. Living in the zone immediately around active vents, they are found in enormous aggregations, thousands of individuals crowded together on chimney surfaces, feeding on the biofilm of chemototrophic bacteria that coats the mineral structures. They appear to lack conventional eyes. The eye stalks visible on the surface of their heads bear no obvious optical structure, but they possess a large paired organ on their dorsal surface that is densely packed with photoreceptor cells sensitive to extremely dim light. Current evidence suggests these organs are capable of detecting the faint thermal radiation emitted by the superheated vent fluid, not visible light but near-infrared radiation, allowing the shrimp to navigate toward and away from the vent using what amounts to a heat-sensing visual organ, in a location where ordinary vision would find almost nothing to work with. Not all hydrothermal vent fluids are hot and laden with metal sulfides, a remarkable class of vent system, alkaline, lower temperature, and chemically quite different from the black smoker type, was discovered in 2000 at a site called the Lost City Hydrothermal Field on the mid-Atlantic ridge. Lost City vents emit fluids with temperatures of around 40 to 90 degrees Celsius, warm rather than burning, and with the highest pH values measured in any natural aqueous environment on Earth. The chemistry driving these vents is not volcanic heat, but a chemical reaction called serpentinization. The reaction of seawater with ancient mantle rock that generates heat, hydrogen, and methane as byproducts. The resulting vent structures are towering white carbonate spires, some approaching 60 meters in height, the tallest known hydrothermal vent structures on Earth. Hosting communities of microbial life different in character from those at high-temperature vents, and generating significant interest among scientists, considering the conditions under which life on Earth may have first arisen. The hypothesis that hydrothermal vents, particularly alkaline vents of the Lost City type, may represent environments analogous to those in which life first originated on Earth, is taken seriously by a significant body of researchers in origin of life science. The key properties that make these environments compelling as life's possible cradle include a steep and sustained pH gradient across the thin mineral membranes of the vent chimneys, which could have functioned as a proton gradient analogous to those used by the first cellular membranes to generate chemical energy, an abundant supply of reduced carbon compounds produced by serpentinization, catalytic mineral surfaces, iron and nickel sulfides that could have promoted the early chemical reactions leading to metabolism, and a temperature environment gentle enough to preserve the first fragile organic molecules while still driving chemical reactivity. None of this is proof that the conditions at modern alkaline vents are the closest natural approximation available to the theoretical environment in which life's chemistry first became self-sustaining. Cold seeps. Areas of the deep seafloor where hydrocarbons and sulfide-rich fluids seep slowly upward through sediments from geological reservoirs below. Host communities with striking similarities to those at hydrothermal vents, but driven by an entirely different energy source and characterized by a very different physical environment. Unlike the hot, turbulent, mineral-precipitating environment of a vent, a cold seep is cool, quiet, and gradual. The fluid emerging slowly enough that there are no visible chimneys, only slow diffuse upwelling through soft sediment. The chemosynthetic microbial communities at cold seeps support ecosystems of mussels, tube worms, chemosynthetic clams, and specialized crabs, all drawing their energy ultimately from the methane and hydrogen sulfide seeping from below. Cold seep communities are typically longer-lived and less dynamic than vent communities. The underlying geological reservoirs are more stable than the tectonic activity driving vents, and the communities that develop over them can persist in relative stability for centuries. Cold seeps. Areas of the deep seafloor where hydrocarbons and sulfide-rich fluids seep slowly upward through sediments from geological reservoirs below. Host communities with striking similarities to those at hydrothermal vents, but driven by an entirely different energy source and characterized by a very different physical environment. Unlike the hot, turbulent, mineral-precipitating environment of a vent, a cold seep is cool, quiet, and gradual. The fluid emerging slowly enough that there are no visible chimneys, only slow diffuse upwelling through soft sediment. The chemosynthetic microbial communities at cold seeps support ecosystems of mussels, tube worms, chemosynthetic clams, and specialized crabs, all drawing their energy ultimately from the methane and hydrogen sulfide seeping from below. Cold seep communities are typically longer-lived and less dynamic than vent communities. The underlying geological reservoirs are more stable than the tectonic activity driving vents, and the communities that develop over them can persist in relative stability for centuries. The mineral deposits produced by hydrothermal vent activity are not purely biological curiosities. Polymetallic sulfide deposits associated with active and extinct vent fields on the mid-ocean ridges contain economically significant concentrations of copper, zinc, gold, silver, and rare earth elements. Concentrated by geological processes over long periods of vent activity into ore bodies that would, in some cases, be worth extracting if they occurred on land. Interest in deep-sea mining of these and other seafloor mineral resources has grown as the demand for metals used in batteries and renewable energy infrastructure has increased. The environmental consequences of mining vent or seafloor environments are a subject of serious ongoing scientific and regulatory debate. Vent communities, while adapted to disturbance and capable of recolonization, depend on specific locations, and the physical destruction of a vent habitat and its associated community may require years to decades for that particular site to recover. If the vent remains active, there is a quality of silence in the idea of a hydrothermal vent community that is different from the silence of the open, deep ocean. The open abyss is silent and empty and cold and dark. The vent is all of those things too. Silent, cold, dark. And yet it is crowded. Life presses against life in the zone where the hot water meets the cold. tube worms brushing against each other in the thermal current, bent crabs climbing over the mineral surface, bacterial mats spreading in dense orange and white sheets across every available substrate. The whole community is alive with a slow chemical urgency. It knows, in the way that all fragile ecosystems know, that the warmth is temporary. The vent will cool. The chimney will collapse. The geological activity will shift elsewhere. And when it does, the larvae of these organisms must have already been dispersed, carried by the faint currents of the abyss to the next warm place, hopefully. Life at the vent does not take its warmth for granted. It simply uses it fully for whatever time is given. The giant squid, Architeuthis dux, is the largest invertebrate known to science by length, with confirmed specimens reaching mantle length of around 2 meters and total length, including the 2 long tentacles, of up to 13 meters. For most of the 20th century, the giant squid was known almost entirely from dead or dying specimens found washed ashore, from fragments extracted from the stomachs of sperm whales, and from sucker scars. Circular, serrated marks found on the skin of those same whales. No living giant squid had ever been photographed in its natural habitat. That changed in 2004 when Japanese researchers Tsunemi Kubadera and Kyoichi Mori obtained the first photographs of a living Architeuthis in the wild, and in 2012 when a live specimen was filmed in the deep Pacific, illuminated by the dim red light of a submersible's camera, moving with a fluid, unhurried deliberateness through water nearly a kilometer beneath the surface. The eyes of the giant squid are the largest eyes of any living animal, measured at up to 27 centimeters in diameter in the largest known specimens, roughly the size of a dinner plate. This extreme eye size is thought to be an adaptation to the conditions of the deep ocean twilight zone through which they transit, rather than the fully dark midnight zone where they spend much of their time. Large eyes gather more light, and in the dim blue of the mesopelagic zone, detecting the silhouette of a predator, specifically the immense silhouette of a sperm whale approaching from above, is a matter of survival. Modeling studies suggest that an eye of this size, in the optical conditions of the deep ocean at depth, would be capable of detecting the bioluminescent disturbances produced by a large swimming whale at distances of perhaps 100 meters or more, enough distance to initiate an escape response before the whale closes. The sperm whale, Physta macrocephalus, is the primary predator of large cephalopods in the deep ocean, diving to depths exceeding 2 kilometers on routine foraging dives, and capable of reaching depths of 3 kilometers or more under extreme circumstances. These dives last up to 90 minutes, during which the whale holds its breath and hunts in complete darkness, using echolocation, producing clicks of extraordinary intensity, among the loudest sounds produced by any animal on Earth, and interpreting the returning echoes to locate and pursue prey in 3-dimensional space. Sperm whale stomachs consistently contain the beaks of giant and colossal squid, the only indigestible remnants of what are otherwise entirely soft-bodied meals, and the presence of sucker scars on the skin of many sperm whales suggests that the encounter between these two animals is not always one-sided. What takes place in the pitch black of the deep ocean between a sperm whale and a giant squid is a drama that no human observer has ever directly witnessed. The colossal squid, Mesonychoteuthis hamiltoni, is distinct from the giant squid, and despite being shorter in total length, is considerably more massive in body weight. Where the giant squid's length is dominated by its long, slender tentacles, the colossal squid has a much more muscular, heavily built mantle and shorter but more powerful tentacles equipped with sharp, swiveling hooks rather than the toothed suckers of Archaeoteuthis. The largest confirmed specimen, caught by a New Zealand fishing vessel in 2007, had an estimated mass of approximately 495 kilograms, making it the heaviest invertebrate ever recorded. The colossal squid is primarily an Antarctic species, found in the Southern Ocean at depths of around 1,000 to 2,200 meters. Like the giant squid, most of what we know about it comes from stomach contents of sperm whales and from the rare accidental capture in deep-sea fishing nets. Its behavior in the wild remains almost entirely unknown. Dragonfish, notably the species Aristostomias scintillans and related members of the family Stomiidae, are among the most fearsome-looking inhabitants of the midnight zone. Their disproportionately large jaws lined with long needle-like transparent teeth, their elongated bodies dark and nearly light-absorbing. Many stomadragonfish carry a bioluminescent barbel beneath their chin, a lure similar in function to the anglerfish's esker, and suborbital light organs that emit red light. Red bioluminescence is a particular specialization of the dragonfish. While most deep-sea organisms are sensitive only to blue and green light and invisible to red wavelengths, the dragonfish appear to have evolved visual pigments capable of detecting red light, allowing them to use red bioluminescence as what amounts to a private channel, a searchlight for prey that the prey themselves cannot see because they lack the visual pigment to detect it. They are hunters in a frequency that the hunted cannot perceive. Marine snow, the continuous, slow fall of organic particles from the sunlit surface ocean down through the water column to the deep seafloor, is the primary source of energy for the majority of deep-sea organisms that do not live near hydrothermal vents. It consists of dead phytoplankton and zooplankton, fecal pellets from surface and midwater animals, gelatinous mucus filtering structures shed by salps and appendicularians, and the aggregated remains of countless surface-dwelling organisms whose lives and deaths occur far above the creatures that ultimately consume their remains. This material sinks slowly, at rates of roughly 10 to 100 meters per day for aggregated particles, and is progressively consumed and reprocessed by bacteria and small invertebrates as it descends, so that by the time it reaches the abyssal seafloor 4 to 5 kilometers below the surface, only a small fraction of the original surface productivity remains. The deep ocean exists on the scraps of the surface world. The barrel-eye fish, Macropina microstoma, carries one of the most extraordinary visual adaptations in the deep ocean. Its most distinctive external feature, its pair of large cylindrical eyes, pointing upward within a fluid-filled, transparent dome that constitutes the top of its head. These eyes are highly sensitive to dim light, and when pointing upward, are optimally oriented to detect the silhouettes of prey or predators against the faint downwelling light from above. For decades, preserved specimens of the barrel eyes suggested that the eyes could only look upward, a puzzling constraint for a predator. In 2009, researchers from the Monterey Bay Aquarium Research Institute observed living barrel eyes in situ and discovered that the eyes can in fact rotate within the transparent dome, swiveling from an upward pointing position to forward facing when the fish move to capture prey. The transparent head, which had always obscured the actual eye position in preserved specimens, had been misinterpreted in every previous anatomical description. The viperfish, Chocladus sloni, is a creature whose anatomy reads like a list of superlatives. Its teeth are so large relative to its skull that it cannot fully close its mouth, the longest fangs curving back past the outside of the head. Its stomach is highly distensible, capable of accommodating prey that approaches the fish's own body length. The first vertebrae behind its head are modified into a shock absorber system that allows the viperfish to ram prey at high speed without injuring itself. It produces bioluminescence along its lateral line, the row of photophores running along its flank, in patterns that may function as counter-illumination or as a species recognition signal in the dark. Viperfish are thought to be ambush predators of the deep scattering layer, rising with it at dusk and descending again at dawn, spending their days in the dim mesopelagic zone and their nights hunting at the surface edge of the midnight zone. Their entire existence is organized around the migration of the animals they depend on at the boundary between the mesopelagic and bathypelagic zones. At roughly 1,000 meters depth, a profound physical change occurs in the water column. Below this depth, the ocean is almost completely isolated from the surface. The water here is old. It was last at the surface hundreds to thousands of years ago, in polar regions where it sank after cooling and becoming dense. It carries with it the dissolved gases and nutrients it contained when it left the surface, slowly depleting its oxygen supply as it travels along the deep ocean circulation pathways. In some ocean regions, the intermediate depths are oxygen minimum zones, regions where dissolved oxygen has been almost entirely consumed by microbial decomposition of sinking organic matter, and where only organisms specifically adapted to low oxygen conditions can survive. These zones act as barriers to vertical migration for many deep-sea organisms, parceling the water column into functional compartments, with different faunal communities separated by the chemistry of the water as much as by depth. Pressure at the depths inhabited by midnight zone organisms reaches levels that would crush the organs of any surface animal within moments. The adaptations that allow deep-sea fish and invertebrates to function normally under these conditions include the elimination of gas-filled spaces, air spaces such as swim bladders, which would be compressed to a fraction of their surface volume at depth, are absent in many deep-sea fish, replaced by tissues with near-neutral buoyancy achieved through fat deposits or the presence of lighter-than-seawater compounds such as wax esters. Cell membranes in deep-sea organisms are modified to remain fluid rather than rigid at low temperatures and high pressures. Different fatty acid compositions maintain the flexibility that membrane function requires. Enzymes at depth are stabilized by small organic molecules called piezolatide. Trimethylamine oxide, or TMAO, is the most widespread that counteract the destabilizing effects of pressure on protein structure. In deep-sea fish, TMAO concentrations increase linearly with habitat depth, suggesting that the deeper the fish lives, the more of this pressure-counteracting compound it requires to maintain normal biochemistry. The midnight zone is the largest inhabited space on Earth by volume. The bathypelagic zone alone, from 1,000 to 4,000 meters depth, covers an area equivalent to the entire surface of the planet and extends 3 kilometers in depth, constituting a volume of water that dwarfs every terrestrial habitat combined. Yet the density of life within it is very low. The extreme scarcity of food, the vanishingly small fraction of surface productivity that reaches these depths as marine snow, means that organisms must cover large volumes of water to encounter enough food to sustain themselves, and most are relatively small, slow-moving, and equipped with metabolisms far more economical than those of surface equivalents. The darkness is not empty, but it is sparse. It is a vast, slow library of specialized lives, each one adapted to a particular dimension of an extreme and energy-limited environment, the whole of it supported by what falls from a world of sunlight far above. There is a particular quality of wonder that the deep-sea creatures of the Midnight Zone seem specifically designed to evoke, a version of wonder that is not the bright, vivid, immediately accessible wonder of a coral reef or a tide pool, but something deeper and stranger. The anglerfish with its dangling light, the vampire squid spreading its webbed arms, the giant squid hanging in the black water with its planet-scale eyes. These creatures are fully real, fully biological, evolved by the same forces that produced every other organism on Earth. And yet there is something about them, the darkness they inhabit, the remoteness of their world, the alien quality of their adaptations, that makes them feel like dispatches from somewhere far beyond the ordinary range of biological possibility. They are not mythological possibility. They are not mythological possibility. They are not mythological possibility B. They are not mythological possibility B. They are not the mythological possibility B. They are not the marsological possibility starst. They are not the they are alive, right now in the darkness below. And the darkness is patient and cold and tremendously, quietly full. Surface ocean currents, those in the upper few hundred meters of the ocean, are driven primarily by the wind, the global pattern of winds, from the trade winds blowing persistently westward in the tropics to the westerlies at mid-latitudes, pushes the surface water into broad rotating systems called gyres. There are 5 major subtropical gyres, one each in the North and South Atlantic, the North and South Pacific, and the Indian Ocean, each rotating clockwise in the northern hemisphere and counterclockwise in the southern, a consequence of the Coriolis effect acting on the moving water. Within each gyre, currents flow along the boundaries, northward on the western side, southward on the eastern, across the top and across the bottom, in a circulation pattern that is not simply a reflection of the wind, but a complex response to the interaction between wind forcing, the Earth's rotation, and the geometry of the ocean basins. The Coriolis effect, the apparent deflection of moving objects caused by the rotation of the Earth, plays a fundamental role in shaping ocean circulation at every scale. A parcel of water set in motion in the northern hemisphere is deflected to its right by the Coriolis effect, in the southern hemisphere to its left. This deflection, continuous and proportional to the velocity of the moving water, means that wind-driven surface currents do not flow exactly in the direction of the wind, but at an angle to it, and in the net, averaged over the depth of the wind-mixed layer, flow roughly perpendicular to the wind direction, in a phenomenon called Ekman transport. It is this transport, applied over the broad areas of the subtropical gyres, that piles water up toward the centers of the gyres, creating small elevations of the sea surface, measurable by satellite altimetry, that drive the geostrophic currents flowing around the gyre's perimeter. The spinning of the planet writes itself into the pattern of every current. The Gulf Stream is the most famous and most studied current in the ocean, a swift, narrow, deep river of warm water flowing northward along the eastern coast of North America, before turning northeastward across the Atlantic toward northwestern Europe. At its strongest, in the Florida Strait, where it is constricted between Florida and the Bahamas, the Gulf Stream transports roughly 30 million cubic meters of water per second, 30 times the combined flow of all the rivers on Earth. The current carries warm, tropical water northward and is the primary reason that the climate of Western Europe is significantly milder than the climate of equivalent latitudes in North America. The warm water slowly releases its heat to the overlying atmosphere, warming the westerly winds that blow across it and then across Europe. Without the Gulf Stream and its associated heat transport, winters in Britain and Scandinavia would be dramatically colder than they currently are. Upwelling zones, coastal and open ocean regions where deep, cold, nutrient-rich water is brought to the surface by wind-driven processes, are among the most biologically productive ecosystems in the ocean, despite being relatively small in area. The most significant upwelling zones are found along the eastern boundaries of ocean basins, the California Current System off the west coast of North America, the Humboldt Current System off South America, the Benguela Current off southwestern Africa, the Benguela Current off southwestern Africa, and the Canary Current off northwestern Africa. In all of these systems, prevailing winds blowing parallel to the coast, in combination with the Coriolis effect, drive surface water away from shore, which is replaced by cold, deep water rising from below. This upwelled water carries dissolved nutrients, nitrate, phosphate, silicate, that fuel explosive growth of phytoplankton at the surface, supporting dense populations of fish, seabirds, and marine mammals entirely disproportionate to the area these zones occupy. The Peru-Humboldt Current System, running along the western coast of South America, supports one of the most productive marine fisheries on Earth. The anchoveta fishery and the extraordinary density of marine life it sustains. Vast schools of anchoveta feed on the phytoplankton fueled by the cold upwelling water. These are in turn consumed by larger fish, seabirds in enormous coastal colonies, and marine mammals. The system is intensely sensitive to the periodic disruption caused by El Niño events, episodes during which the trade winds that normally drive the upwelling relax. Warm water flows eastward across the Pacific, and the cold upwelling water is suppressed. During strong El Niño events, the anchoveta population collapses, and the cascading effects, seabird starvation, marine mammal mortality, fishery failure, ripple through the food web and the economies of the coastal nations that depend on it. The productivity of the upwelling zone is immense. Its vulnerability to a change in wind direction is equally so. Internal waves, waves that travel along density boundaries within the ocean, invisible at the surface but sometimes hundreds of meters in amplitude within the water column, are one of the less visible but dynamically important features of ocean circulation. Where two layers of water of different density meet, at the thermocline or at density boundaries in the deep ocean, disturbances can generate waves that propagate along that interface in the same way that surface waves propagate along the boundary between water and air. Internal waves can carry enormous amounts of energy across ocean basins, and when they reach shallow water or the continental slope and break, they produce intense turbulent mixing that transfers nutrients from deep to shallow water, drives sediment transport along the seafloor, and provides one of the primary mechanisms for mixing across the thermocline that supplies the sunlit surface ocean with nutrients from below. They are invisible from above, undetectable without specialized instruments, and energetically fundamental to the ocean's biological productivity. Langmuir circulation is a pattern of organized, helical circulation cells that develops in the wind-mixed surface layer of the ocean under sustained wind forcing. Under appropriate wind speeds, The surface layer of the ocean organizes into a series of counter-rotating pairs of helical rolls, aligned with the wind direction. The rolling motion brings surface water downward along convergence lines and upwells deeper water along divergence lines, creating long parallel streaks of foam and floating material at the surface that mark the downwelling convergence zones. These streaks, visible from the deck of a ship in the open ocean as long, orderly lines of bubbles, seaweed, and debris, are the surface expression of the rolling structure beneath. Langmuir cells play an important role in mixing heat, gases, and materials through the wind-mixed layer, and in concentrating floating organisms and particles along the convergence lines, where they become accessible to birds and fish feeding at the surface. Tidal currents, the water movements generated by the periodic rise and fall of the sea surface in response to the gravitational pull of the moon and sun, can be extremely powerful in coastal and shelf environments where the tidal range is large and the water is constrained by geometry into narrow channels. In the Bay of Fundy, between Nova Scotia and New Brunswick, the tidal range exceeds 16 meters, the largest in the world, and the currents generated as this enormous volume of water moves in and out of the bay can reach several knots. Tidal currents in channels and straits mix the water column, preventing stratification, transporting sediment, and creating the turbulent, oxygen-rich, nutrient-mixed environments that some of the most productive coastal ecosystems depend on. The mechanism behind the extreme tidal range at Fundy involves resonance. The natural oscillation period of the bay happens to be close to the tidal period, so the system amplifies the ocean tide in the same way that a pendulum responds most strongly to a driving force that matches its natural frequency. The Antarctic circumpolar current, flowing eastward around the continent of Antarctica, driven by the persistent westerly winds of the Southern Ocean, is the world's largest ocean current by volume transport, carrying roughly 130 to 150 million cubic meters of water per second around the continent in a continuous loop. Unlike every other major ocean current, the Antarctic circumpolar current encounters no continental barrier. It encircles an entire hemisphere of open ocean, and this unobstructed path allows it to maintain its energy over centuries without dissipation against a continental boundary. The Southern Ocean is also the primary engine of the global thermohaline circulation. It is here, around the margins of Antarctica, that the densest deep water in the ocean forms as sea ice rapidly freezes and releases brine, creating Antarctic bottom water that sinks to the seafloor and spreads northward through the Atlantic, Indian, and Pacific basins, ventilating the deep ocean with the cold, oxygen-rich water that sustains life throughout the abyss. Mesoscale eddies, rotating bodies of water roughly tens to hundreds of kilometers in diameter, that spin off from major boundary currents and drift slowly across the ocean basins, are one of the dominant features of ocean circulation at scales relevant to biological productivity. They form where currents become unstable, pinching off into isolated rotating disks of water that carry the properties, temperature, salinity, nutrient content, biological community, of their origin current into the surrounding water. Warm core eddies spun off from the Gulf Stream carry warm, low-nutrient Sargasso seawater into the colder, more productive waters of the continental shelf, while cold core eddies carry productive shelf water into the Sargasso. Eddies can persist for months to years, their rotating structure maintaining a semi-enclosed environment that becomes a distinct ecological unit, sometimes supporting elevated biological productivity within the eddy, sometimes creating refugia of warm or cold water that transient marine animals exploit during migration. The Sargasso Sea, located within the North Atlantic subtropical gyre, enclosed by the Gulf Stream to the west, the North Atlantic Current to the north, the Canary Current to the south. The Canary Current to the south is unique among the world's seas in having no land boundaries. It is defined entirely by the ocean current surrounding it, and it is named for the vast quantities of floating sargassum seaweed that accumulate within its calm, warm gyre center. The sargassum forms a complex, three-dimensional habitat for an extraordinary community of organisms that live exclusively in this floating ecosystem. Small fish, crabs, shrimp, nudibranchs, and other invertebrates that are camouflaged to match the golden brown weed they inhabit, and that would be exposed prey in open water. The Sargasso Sea is also the spawning ground of the European and American eel, both species making extraordinary migrations of thousands of kilometers from their freshwater homes to spawn in these calm, warm waters, their larvae drifting back on the currents. The Mariana Trench was formed at a subduction zone, a convergent plate boundary where one tectonic plate descends beneath another into the Earth's mantle, driven by the density difference between older, cooler oceanic crust and the mantle beneath it. The Pacific Plate, the File-Brains Plate, into the Tidey, one of the largest on Earth, is being subducted beneath the smaller Mariana Plate at a rate of roughly 2 to 3 centimeters per year. Slow by human standards, but geologically brisk, generating significant seismic and volcanic activity along the associated island arc system. As the Pacific Plate bends downward, it creates the characteristic V-shaped cross-section of a deep ocean trench. Steep, narrow, and asymmetric, with the subducting plate forming one wall and the overriding plate the other. The Mariana Trench extends for roughly 2,550 kilometers in length and averages about 69 kilometers in width. Long and narrow, like a scar in the seafloor, recording the ongoing collision of two of the largest pieces of the planet's outer shell. The first systematic measurement of the Mariana Trench's depth was carried out by HMS Challenger, the British naval corvette that conducted the pioneering global oceanographic expedition of 1876, which gave the Challenger Deep its name. Using a hemp-sounding line with a heavy weight, the Challenger crew measured depths in the area that were unprecedented for their time, recording values of approximately 8,180 meters. Modern measurements using multi-beam sonar and pressure-sensitive instruments have established the maximum depth of the Challenger Deep at approximately 10,935 meters, with some surveys yielding slightly different values depending on the precise definition of the reference point and the measurement methodology. The uncertainty in the depth of the deepest point on Earth, the vagueness of a measurement conducted at the bottom of nearly 11 kilometers of water, is itself a small testament to how difficult the deep ocean continues to be to observe with precision. The first crewed descent to the bottom of the Challenger Deep was made on January 23, 1960, by the Swiss-designed US Navy-operated Bathyscaphe Trieste, carrying oceanographer Jacques Piccard and US Navy Lieutenant Don Walsh. The descent took approximately 4 hours and 53 minutes. The return journey, 3 hours and 17 minutes. At the bottom, Piccard and Walsh observed a flatfish resting on the sediment, an observation later disputed on taxonomic grounds, with some researchers suggesting the animal was more likely a sea cucumber or a polychaete worm. But other organisms, including shrimp, were also observed, establishing beyond question that life persisted even at full ocean depth. Their time at the bottom was brief, and the view through the small quartz viewport revealed a featureless sediment-covered floor, illuminated by the Trieste's lights, quiet and pale and almost indistinguishable from any other stretch of abyssal seafloor, save for the weight of 10 kilometers of water pressing down from above. In 2012, filmmaker and explorer James Cameron made a solo descent to the Challenger deep in the specially designed submersible deep-sea Challenger, becoming only the third person to have reached the bottom and the first to do so alone. The deep-sea Challenger was a radical departure from the conventional submersible design, built as a vertically oriented torpedo shape to minimize the descent and ascent time through the water column, and equipped with a foam syntactic material of sufficient density to resist compression at full ocean depth. Cameron spent approximately 3 hours at the bottom before a hydraulic leak forced an early ascent, but the dive produced scientific samples and high-definition video footage of the Huddle seafloor, significantly advancing the documentation of the Challenger deep environment. The submersible, retired after the dive, was donated to the Woods Hole Oceanographic Institution for scientific purposes, the dominant animals of the Huddle zone. The term applied to the environment within ocean trenches below roughly 6,000 meters are not the exotic monsters of popular imagination, but are, for the most part, small, pale, and deceptively ordinary. In appearance, amphipods, crustaceans related to the sand fleas commonly found on beaches, but here reaching lengths of up to 30 centimeters, are among the most abundant Huddle organisms, found in extraordinary densities in baited traps deployed to the floor of the Mariana and other deep traps. They arrive at bait within hours of its placement, crowding the trap frame in numbers that suggest populations far more substantial than the sparse food resources of the Huddle zone might suggest. Their abundance is explained partly by the topography of the trench itself. Organic material sinking through the water column is funneled into the narrow depression of the trench floor by gravity, concentrating food energy in the deepest points to a degree greater than on the surrounding abyssal plain. The snailfish, members of the family Liparidae, have been recorded as the deepest living vertebrates on Earth, with specimens of Pseudoliparus wirae photographed and captured at depths exceeding 8,000 meters in the Mariana Trench. They are small, translucent, gelatinous in texture, and superficially fragile looking. Not what intuition would suggest for the champion vertebrates of depth. Their success at extreme depths reflects a set of biochemical and physiological adaptations refined over millions of years of Huddle existence. High concentrations of TMAO stabilizing their enzymes against pressure denaturation. Cell membranes with lipid compositions, maintaining fluidity at low temperatures and high pressures, and a body plan that, absent a swim bladder or mineralized bones, is not fundamentally compromised by the loads that crush rigid, gas-filled structures. They have been filmed moving actively, feeding on amphipods, and displaying the behaviors of healthy, well-provisioned fish, because at the bottom of the Mariana Trench, if the biology supports it, life is simply life. Holothurians, sea cucumbers, are among the most visually conspicuous organisms of the Huddle and abyssal seafloor, sometimes present in such numbers that they dominate the visual field seen from a submersible traversing the trench floor. They move slowly across the sediment surface, ingesting sediment and extracting organic material from it, a form of deposit feeding that makes them, in their slow and undramatic way, among the most important processors of organic material on the deep seafloor. Some Huddle holothurian species have been observed in aggregations of hundreds of individuals, gathered around concentrations of food-rich sediment their pale, elongated bodies arranged in loose groups over the seafloor. Their abundance at such extreme depths, where food is scarce and conditions extreme by any surface standard, reflects the degree to which the soft-bodied body plan, with no gas spaces and no rigid structures to betray it under pressure, is suited to the fundamental physical demands of the Hadal environment. The sediment at the bottom of the Challenger Deep is composed partly of the accumulated remains of the planktonic organisms that have sunk from the surface for millions of years. Foraminifera tests, diatom frustules, coccolithophore, plates, and partly of terrigenous material washed from the surrounding islands and continents by rivers and wind. This sediment record is extraordinarily valuable to paleoceanographers, the layered archive of biological and chemical material preserved in deep-sea sediment cores can be read as a record of surface ocean conditions extending back tens of millions of years, capturing changes in temperature, productivity, chemistry, and biology across the span of time recorded in the deposit. The slowness of sedimentation in the deep trench, perhaps a few millimeters per 1,000 years, means that even relatively thin sediment cores reign that span considerable geological time, each layer a sample of the ocean surface as it was when those organisms were alive. In 2018, researchers using remotely operated vehicles in the Mariana Trench recovered amphipods from the Challenger Deep containing measurable concentrations of polychlorinated biphenyls and polybrominated dipenyl ethers, persistent organic pollutants banned from manufacture in many countries, but still circulating in the ocean from legacy industrial sources. The concentrations found in the Hadal amphipods were, by some measures, higher than those found in crustaceans from one of the most polluted rivers in China. The finding demonstrated that the deep ocean, the most remote, least accessible, most removed from direct human activity of any environment on Earth, is not insulated from the chemical outputs of human civilization. Pollutants, produced at the surface, are absorbed by organisms in the surface ocean, incorporated into biological tissue, packaged into sinking particles through the biological pump, and delivered to the Hadal zone by the same marine snow that carries organic matter to the deep. The deepest place on Earth is not beyond reach. The geological environment within the Mariana Trench is not uniformly sediment-covered. Exposed rock outcrops occur on the steep inner walls of the trench, revealing layers of seafloor crust and mantle rock that have been brought to the surface by the bending and faulting of the subducting plate as it flexes downward. Serpentinized mantle rock, the same material that drives alkaline hydrothermal vent chemistry at Lost City, has been found on the trench walls, along with chemosynthetic communities similar in character to those at cold seeps, sustained by the methane and hydrogen generated by serpentinization of the exposed mantle peridotite. The trench is thus not only a topographic feature of the deep ocean, but a cross-section through the Earth's oceanic crust, a place where material from many kilometers below the seafloor is exposed at the surface, offering geologists direct access to rocks that would otherwise be inaccessible, except through drilling. There are dozens of Hadal trenches distributed around the margins of the Pacific, Indian, and Atlantic Ocean basins, each associated with a subduction zone, each reaching depths that classify it as Hadal. The Tonga Trench in the southwestern Pacific reaches a depth of approximately 10,820 meters. The Philippine Trench reaches approximately 10,000. The Kuril-Kamchatka Trench in the northwestern Pacific reaches approximately 10,500 meters. Each trench is a geographically isolated deep environment, separated from other trenches by the broad abyssal plain. And this isolation has driven the evolution of distinct hadal-faunal communities in different trenches, species found in the Mariana Trench that differ from those in the Tonga Trench, despite the broadly similar physical conditions. The hadal zone, despite its depth and its apparent uniformity, is biologically diverse at the regional scale, the isolation of each trench functioning as an evolutionary engine in the same way that island geography drives speciation above water. To descend, in imagination, to the floor of the Challenger Deep is to arrive somewhere that most of the human sensorium cannot interpret. There is no light, there is no sound of consequence. The pressure is beyond any bodily reference point. The temperature is just above freezing. The floor is soft sediment, pale in the beam of a light, extending to a horizon that is only a few meters away in the dark. And yet what lives here, the amphipods in their hundreds, the pale holothurians moving unhurriedly across the sediment, the snailfish hunting by mechanosensory perception in the lightless water above the floor, is not somehow lesser life for having been reduced to this. It is life that has gone all the way to the bottom of the world's ocean and found a way to exist there, to find food, to move, to reproduce, to be. The deepest place on Earth is not a place of absence. It is simply a place where life, finding no reason not to, continues. The ocean absorbs approximately 25 to 30% of the carbon dioxide that human activity releases into the atmosphere each year, a service of extraordinary importance whose full scale is only appreciated when you consider how much higher atmospheric CO2 concentrations would be in its absence. This absorption occurs partly through the direct dissolution of CO2 into seawater at the surface, the ocean and atmosphere constantly exchanging gases across their boundary, the ocean taking up the excess, and partly through the biological pump, the photosynthesis of phytoplankton which fixes atmospheric CO2 into organic matter, some of which sinks to the deep ocean and is removed from the active carbon cycle for centuries to millennia. The ocean's carbon uptake has buffered the pace of climate change, but at a cost. The dissolved CO2 forms carbonic acid, gradually acidifying the ocean surface and threatening the calcifying organisms, mollusks, corals, echinoderms, that build their bodies from calcium carbonate. The ocean is also the source of the majority of the water that falls as rain and snow on the land surfaces of the Earth. Solar energy evaporates vast quantities of seawater from the ocean's surface into the atmosphere. Approximately 430,000 cubic kilometers of water per year, where it condenses into clouds, is transported by atmospheric circulation over the continents and falls as precipitation. The rivers that drain the land gather this water, along with dissolved minerals from the rocks they traverse, and return it to the ocean, completing the hydrological cycle that has connected the sea to the land since the first rains fell on the early Earth. Every river is an extension of the ocean. Every cloud above a continent is, in a direct physical sense, re-evaporated seawater on its way back. The water that falls on mountains and grows forests and fills reservoirs was ocean water not long ago and will be ocean water again, cycling through the planetary system with the patience of deep time. The blue whale, Balaenoptera musculus, is the largest animal known to have ever existed on Earth, reaching length of up to 30 meters and weights of up to 200 tons, heavier than any dinosaur for which we have reliable size estimates. It achieves this mass by consuming one of the smallest prey items in the ocean. Krill, small crustaceans, typically 1 to 5 centimeters in length, which it engulfs in enormous mouthfuls of water filtered through baleen plates. During the Antarctic summer feeding season, a large blue whale may consume 4 to 6 tons of krill per day. The evolution of such extreme body size in baleen whales is thought to be enabled by the ocean's provision of food energy in vast, dense aggregations. Schools of krill concentrated by upwelling and by biological aggregation behavior into patches exploitable by lunge feeding, and by the buoyancy of seawater, which remove the structural constraints that gravity imposes on the bodies of large terrestrial animals. Whale song, particularly the extraordinarily complex, low-frequency vocalizations produced by humpback whales, is one of the most studied and least fully understood forms of animal communication. Male humpback whales produce song during the breeding season. Long, structured sequences of sounds, organized into phrases and themes that are repeated, modified, and shared across populations. All males in a given ocean basin tend to sing the same song at any given time, and the song evolves progressively across the breeding season. New phrases are introduced, old ones dropped, innovations spreading from singer across the population. Individual blue whales produce calls in the infrasound range, below 20 Hz, below the threshold of human hearing, so low in frequency that they can travel thousands of kilometers through the deep sound channel before dissipating. In the pre-industrial ocean, before shipping noise raised the ambient acoustic floor, blue whale calls may have been detectable across entire ocean basins. The deep sound channel, the SOFAR channel for sound fixing and ranging, is a layer within the ocean, typically between 600 and 1,200 meters in depth, where the speed of sound reaches a minimum. Sound waves propagating through the ocean are refracted toward regions of lower sound speed in the same way that light is bent at optical boundaries, and the OFAR channel acts as a waveguide. Sound originating near the channel is refracted back toward it rather than escaping upward or downward, and can travel enormous distances with relatively little attenuation. Low-frequency sounds, including blue whale calls, and the acoustic signals of underwater earthquakes, can propagate through the OFAR channel for thousands of kilometers. The US Navy exploited this property during the Cold War for long-range acoustic surveillance. Marine biologists use it to track the movements and calls of large whales, and oceanographers use sound propagation through the ocean water column to measure ocean temperature changes with extreme precision. Sea turtles, 7 species surviving from a lineage that traces back more than 100 million years to the age of the dinosaurs, navigate the open ocean using a mechanism whose precision continues to astonish researchers who study it. They are capable of detecting both the intensity and the inclination angle of the Earth's magnetic field, and use this information to determine their position on a magnetic map of the ocean, effectively reading the magnetic field as a coordinate system and correcting their course toward a target location. Female sea turtles return to nest on the same beaches where they were born, sometimes crossing thousands of kilometers of open ocean to do so, guided by an internal magnetic map that appears to encode the specific magnetic signature of their natal beach. The magnetic field at any given location changes slowly over time due to geomagnetic drift, and long-term population studies suggest that the nesting site preferences of turtle populations shift gradually in response to these magnetic changes, the turtles tracking their birth location as its magnetic signature slowly moves. The migration of the Arctic tern, a seabird rather than a strictly marine animal, but one whose life is almost entirely defined by the ocean, is the longest known migration of any animal on Earth. Arctic terns breed in the Arctic during the Northern Hemisphere summer and winter in the Antarctic during the southern hemisphere summer, traveling a round-trip distance of roughly 70,000 kilometers each year, over a lifespan of perhaps 30 years. An individual Arctic tern may travel the equivalent of 3 trips to the moon and back. The route is not a straight line, but a figure of 8, tracking the prevailing winds. The tern exploiting the global wind systems to minimize the energetic cost of the journey. The bird follows summer from pole to pole, experiencing more hours of daylight in a single year than any other animal on Earth. Its life a continuous trailing of light across the surface of the world's oceans. Kelp forests, dense underwater canopies of giant kelp, Macrocystis, Pyrifera, growing from the seafloor to the surface in cold, nutrient-rich coastal waters, are among the most structurally complex and biologically diverse marine habitats in the temperate ocean. Giant kelp is one of the fastest-growing organisms on Earth, adding up to 60 centimeters of new frond per day under optimal conditions, and forming canopies reaching 20 to 30 meters in height above the seafloor, taller than most terrestrial trees. The structural complexity of the kelp forest creates a layered set of habitats exploited by different organisms at different levels. The canopy, the midwater column, the stipe zone near the seafloor, and the seafloor itself. Sea otters, which historically maintained kelp forest ecosystems by preying on urchins that would otherwise graze the kelp to its base, are among the most widely cited examples of a keystone species. Their presence or absence determines whether the ecosystem exists in its forested or urchin-barren state. Ocean noise pollution. The increase in ambient underwater sound levels caused by shipping traffic, seismic surveying, military sonar, and industrial construction has measurably altered the acoustic environment of the ocean over the past half-century, with significant documented effects on marine mammals that rely on sound for communication, navigation, foraging, and reproduction. Low-frequency shipping noise has raised background noise levels in many parts of the ocean by 10 to 20 decibels since the mid-20th century, equivalent to a tenfold increase in acoustic energy. This elevation of background noise reduces the effective communication range of large whales, potentially interfering with the maintenance of social bonds, the coordination of feeding behavior, and the finding of mates across the great distances of the open ocean. Military sonar exercises have been associated with mass strandings of beaked whales. Seismic surveys produce acute sound exposures that have been shown to disrupt feeding and alter the distribution of commercially important fish species over large areas. Marine protected areas. Regions of the ocean where human activities including fishing, mining, and development are restricted or excluded, have demonstrated significant ecological benefits in well-designed and adequately enforced implementations. Within fully protected no-take reserves, fish populations recover in biomass and in species diversity within years to decades, and the effects spill over into adjacent unprotected areas as the increased productivity of the reserve exports larvae and recruits to surrounding waters. The ocean's capacity for recovery, given sufficient protection from direct exploitation, can be rapid relative to the long timescales of the processes that formed its geology. Species that have been absent from a region for decades can return within years if the food web structure allows it. And habitats degraded by physical disturbance can begin structural recovery within a season. The key constraint on this recovery is not biological. It is institutional, creating, resourcing, and enforcing the protections that would allow the ocean to demonstrate what it can do when left largely alone. Seagrass, mangroves, and salt marshes, collectively called blue carbon ecosystems, for their disproportionate capacity to sequester and store carbon relative to their area, cover only a small fraction of the ocean and coastal zone but sequester carbon at rates per unit area that can exceed those of tropical rainforests. Mangroves in particular store carbon at high rates in their waterlogged, low-oxygen sediments where the slow decomposition of organic matter allows carbon to accumulate over centuries. Salt marshes export dissolved organic carbon offshore to the deep ocean through tidal exchange, transferring it from an environment where it might be quickly respired to one where it settles into permanent storage in deep-sea sediments. The loss of these ecosystems through coastal development, sea level rise, and land use change releases the stored carbon back into the atmosphere, making their conservation not only a matter of biodiversity, but of climate stability. The smallest coastal habitats carry some of the largest planetary stakes. The leatherback sea turtle, the largest living turtle species, reaching shell lengths exceeding 1.8 meters and masses exceeding 600 kilograms, undertakes one of the most energetically demanding migrations in the animal kingdom, crossing the Pacific between foraging grounds along the coast of California and nesting beaches in Indonesia and Papua New Guinea. The Pacific leatherback population has declined by more than 90% since the 1980s, driven by bycatch in fishing gear, egg collection, coastal development of nesting beaches, and the ingestion of floating plastic debris, which leatherbacks cannot distinguish from the jellyfish they feed on. The leatherback's extraordinary morphology reflects millions of years of evolutionary refinement. Its shell is not a rigid bony structure like that of other turtles, but a flexible leathery carapace reinforced by thousands of tiny bone fragments embedded in the skin, now settle, allowing the body to flex under pressure as the turtle dives to depths exceeding 1,000 meters in pursuit of jellyfish in the cold, deep water off the continental shelf. Human beings have lived on and by the sea for as long as our species has existed, and possibly longer, given evidence of marine resource exploitation by archaic hominins at coastal sites in South Africa dating to more than 100,000 years ago. The ocean has been a source of food, a highway for trade and migration, a barrier and a connector, a source of mythology and metaphor, and spiritual significance across every culture that has ever had access to it. The nautical technologies developed by Polynesian navigators, outrigger canoes capable of crossing thousands of kilometers of open ocean, navigational methods using stars, swells, birds, and bioluminescence, represent one of the greatest achievements in human technological and intellectual history, enabling the colonization of the Pacific Islands by a seafaring civilization that read the ocean as a landscape rather than a void. The sea has always been both the most dangerous and the most navigable of the Earth's natural features. The response of every maritime culture has been eventually to go. The sound of the ocean, specifically the low-frequency sound of surf at a shallow to moderate distance, or the gentle wash of water in enclosed spaces, is reliably associated with reduced physiological stress in human subjects across a wide range of studies measuring cortisol levels, heart rate, and self-reported anxiety. The mechanism is not fully elucidated, but the sound spectrum of surf, a broadband noise with energy concentrated in frequencies below a few hundred hertz, with a rhythm of arrival and recession, has been proposed to act as a natural version of white or pink noise, masking higher frequency acoustic disturbances while providing a rhythmically predictable auditory pattern that the brain can track without effort. The evolutionary hypothesis is that the sound of the sea may carry associations: safety from pursuit, proximity to water and food resources, deep enough in the human past that they have been partially encoded as a calm-inducing acoustic signature. Whether or not this explanation is correct, the fact is simple. The sound of the sea helps people sleep. The ocean is older than the continents in their current form, older than the oldest rock exposed at the Earth's surface. It has been here through the assembly and breakup of supercontinents, through the mass extinctions that ended the Permian and the Cretaceous, through the snowball Earth, episodes when ice may have covered the ocean's surface to the equator, through the evolution of the first cells, the first photosynthetic organisms, the first multicellular animals, the first fish, the first creature that climbed out of it onto land and became the long, complicated chain of evolutionary experiments that eventually produced us. The ocean was here before we were and will be here after we are gone. Not indifferent to us exactly, because indifference requires a kind of awareness, but simply continuous, carrying on the vast, patient, chemical and biological and physical business of being an ocean on a water world, in the outer arm of a spiral galaxy, for as long as the physics allows. And so we surface, slowly as always. The pressure releasing, the light increasing, the blue growing lighter and lighter until you can see the shimmer of the surface above you. And then the sky. You have been a long way down tonight. You have visited the coral polyps secreting their patient limestone cathedrals. You have watched the dinoflagellates spark in the breaking waves. You have been in the darkness with the anglerfish and its cold blue light. You sat, briefly, at the floor of the Mariana Trench and watched the amphipods move through the sediment. You heard, in the register of understand rather than of sound, the long, low, 1,000-kilometer call of a blue whale moving through the deep sound channel in the dark Pacific. All of this is real. All of it is happening right now, in the ocean outside whatever window is nearest to you. Or if no ocean is near, then in the ocean that lies beneath the sky above you. Connected to every other ocean by the continuous body of water that covers most of this planet's surface and has covered it for 4 billion years. You are made of water. A substantial fraction of you is ocean chemistry. The same salt concentration, the same mineral composition, the same slow solvent of life. The ocean is not foreign to you. You carry a version of it in your cells, in your blood, in the fluid that washes around your brain as you slowly now approach sleep. The tide will come in and go out again. The gyres will complete their slow, gyre-shaped circuits. The vent will continue its patient chemistry in the abyss. The sea turtle will navigate by the field of the earth, and you will sleep now, here, on the surface of a water world. The ocean is close. Let it hold you.